So today we're going to be talking about convolutions, which I believe is what you learned about this week. As you learned in class, convolutions are an efficient way to extract information from image like data. There today we'll do two things with this. So the first one is that we'll get a better sense for what convolutions are like in higher dimensions. And this is very helpful because when we're actually working with neural networks, they tend to be quite large and we tend to be passing around all sorts of like different dimensional kernels and input data. So I think visualizing this at least once is very helpful. And then I think this is really great, and this is something that Karthik did last year for the demo, is that oftentimes, like in the way that I learned about convolutions, I was told like, oh, if you pick the kernel filter like this, then you can detect like vertical edges or horizontal edges or circles or things like that. And I was just told like, okay, that's actually what, or something like that is what happens in deep learning models when we train them a lot. But I didn't see that in practice. So it's actually not that hard, and we'll do it today. We'll visualize the kernels that are learned by models, and we'll apply them directly to images, and that'll be very satisfying because it's not just like, in theory, this is what convolutions allow us to do. It's like, here are actual places where we can, or like these are actual learned kernels, and these are what the kernels are doing. Okay, so that's what our goal is for today. Let's jump into the first part of this. So we'll be doing convolutions in higher dimensions. So that I can talk through this, I'll be just copying a bunch of these images and then we can discuss them. These are from the textbook DL2, DTL, Deep Learning, the Deep Learning textbook for this class. And that's where I got these images from. So in class, I believe you learned about the standard convolution. In the simplest case, the input image, this thing on the left, has a single channel. Here, a single channel just means that it's like a single pixel value in each one of these different cells. So it's a matrix, and there's only one matrix, corresponding to the fact that we only look at a single color here. So in this case, we'd interpret that as a grayscale image. And so we have a single channel input and a single channel output. To produce one of these pixels, the way we do it, so it's highlighted in blue, is that we take a kernel of some size, here it's 2 by 2, and we apply it to like each one of the different places that we could place it within the input image. So here we could do it in the top left corner, and we multiply each one of these values together. So it's 0 times 0, 1 times 1, 3 times 2, and 3 times 4. So I think this is 6 plus, or no, yeah, 6 plus 12, which is, oh, and plus 1 up here. Okay, yeah, so that's how we get to 19. And this is the like standard convolution. When we're thinking about this, we say that we have a 3 by 3 dimensional input involved with a 2 by 2 dimensional kernel, and this gives a 2 by 2 dimensional output. Of course, we can do this in higher dimensions, which is what we're going to do when we build neural networks. So we can have multiple channels as input. This would correspond to the case that we have more than just a single color. So when we represent color images in color, we use 3 different colors, so red, blue, and green. And for each one of them, we have an associated matrix. So here it's not 3 channels, which we'd have if we had a like image in color. We have 2 different channels, and that just means that we have a matrix. We have 2 different matrices, and 2 here is the number of channels. When we have something like this, we need the number of channels to match the number of kernels that we have, because what we're doing is we take one of these kernels, right? So here we have 3 by 3 dimensional input, and we can involve it with 2 by 2 dimensional kernels. What we do here is we take this first kernel and we apply it to the first channel in the input, just as we did in the standard case. Then we take the second kernel and we apply it to the second channel in the input, just as we did up here. And this, so if we were to like do this operation out, it's equivalent to the thing we get on the right, which is what's going on right here. And we add up the corresponding pixel values that we get. So if you did the algebra and the calculations, you should get the corresponding value in this top left area is 56. Any questions on this, like multiple channels input idea? Okay. Uh, so here, the like key takeaway is that the number of channels needs to match the number of kernels that we have. So if we have two channels, we need to have two kernels, and this is because each like kernel belongs to a certain one of these input channels. And then, of course, I'm glossing over this, but there are lots of ways that you could like apply the kernel to the actual input. You could have like some buffer on the edge, which you apply it to, or you could like space out the way you apply it to. But for simplicity, I'll just talk about like the standard way to apply this convolution here. Now that we've talked about multiple channels as input, let's talk about multiple channels as input and output, which is what we actually do in these neural networks. And the idea is the same, except now we'll have two different sets of kernels. So here we can think about it as analogous to the first multiple channels in case that we described up here, where we have a 3 by 3 by 3 input. So we have three different matrices. Each matrix is 3 by 3. And we convolve it with two sets. Each set has three kernels. And the dimension of one of these kernels, I don't know why I said 2 by 3. Let's make it 2 by 2. Sorry. Okay, yeah. So, and we two sets of three kernels, and each kernel has 2 by 2 dimensions in it. Here to get the 2 by 3 by 3 dimensional output, we'll have to like add some spacing to get it to line up. But the like important idea is that if you want, so we saw here we can go from multiple channels to a single output channel using one set of kernels. So the number of kernels here is just the number of input channels. That's the same idea here. We need this 3 to match the dimension of the input channel. That has to be the same because we have one kernel for each one of the channels. And then this dimension here, this is the number of kernel sets that we apply, matches the output size of the number of output channels that we have. Okay, I'll pause here and see if there are any questions. It's kind of a weird concept at first, but I think it's very helpful to think about this in this iterative fashion where we go from like a single standard convolution to this more generalized form, we have multiple channels as input, to a slightly more general form, we have multiple channels as input and multiple channels as output. Okay, so now that we have a little bit of an understanding of the way we apply convolutions in practice when we have lots and lots of data and big networks, let's visualize a particular neural network or convolutional neural network, which is called AlexNet. AlexNet was like won this big competition in the early 2010s, and it did it by like just being very, very large and using convolutions. And it was able to use that computational capacity by like a clever use of GPUs. And I think this is one of the first neural networks that actually use GPUs, and that kind of started the like, deep learning progression that we've seen today, where we are able to like train and use such big models because we know that GPUs are very good at matrix multiplication. Okay, so there's a little bit of history behind the particular model that we'll be seeing today. And when it performed in the competition, it did way, way better than everything else. It like had way more accuracy than all the other things in the model, or all the other things it was competing against. And it was kind of a wake-up call for people that like deep learning is very effective and it can be done like maybe not efficiently, but in a reasonable amount of computational, with a reasonable amount of computational resources. Okay, To use this, we'll need to import a bunch of libraries. Yeah, okay, excellent. And the first thing that we're going to do is also, I'm gonna like define some functions for plotting. I don't, it's not so important that you understand the way, like you will understand what these are doing in a second, and it's not important that you understand this code because we'll just be using this for like plotting something, which I'll describe in a second. We'll two different, um, load two different versions of AlexNet. We'll have a trained version, so it's been trained on lots and lots of data, and it works very well. And we'll have an untrained version, which is randomly initialized. To do this, I'll use specific code based on the different libraries that I just imported. So in practice, if you're doing this, you just look it up. So to load AlexNet, I can load it by using the Torch Vision libraries, looking at the models that they have, and then calling AlexNet. If I call it without any parameters, then this is the untrained version of it. And then I'll do the same thing, except I'll get the like pre-trained version. And I'll just call it with a different set of like parameters here. And that's just that we have default weights. And here that's just an artifact of however they set up the function. I'll call it something else. I'll call it AlexNet pre-trained. And you can see this is very, very large. I think that's like 233 megabytes of weights, which is a very big model. So let's take a look at it. Generally, if you have any model that you're loading, you can actually just call print on that model. When you do that, you get something that's kind of gross. Here, this is describing the like different layers that we have. And like it's doing it in sequence. So the first thing we do is apply this like two-dimensional convolutional layer. We specify the kernel and the stride and all these other things. This is kind of hard to parse itself, but we can do something that's slightly more pretty by using a torch summary package. So I'll say we use the torch summary package to get a nicer output to understand the layers here. Notice that so far we've worked with neural networks that take in a single like type of dimension as input. That's because like we literally had like in the standard neural network that we've seen so far, you need to have exactly the right number of features because then you apply a linear layer to it, and the number of weights that you have depends on the number of features that you started with. That's no longer the case with convolutions because the weights that we have are the size of these kernels. So in this input image, I could apply the same like two kernels, each of 2 by 2 dimensions to a different sized input image. It wouldn't matter if this were like two channels of 4 by 4, for example. I'd apply the exact same operation to it. It's just the only thing that would be different is the output size would be different. But AlexNet was coded in such a way that it almost doesn't matter the input dimension that you're using. Actually, it might matter for, no, yeah, it doesn't matter because the only things that are fixed are the size of the kernel. So you just need to get the like number of dimensions or the number of channels, right? Which I think is just 3 channels, which is very standard for having color images. But yeah, so that is to say that the size of each one of these input and outputs from each one of these layers depends on the size of the input to your neural network, which is kind of a strange concept and is specific to convolutional layers because the things that we're training here are the weights in the kernels, not weights that depend on the like actual dimension of the input. Okay, so that's all to say that we need to specify the size of the input. And here we'll imagine that we have a 3 times 224 by 224 dimensional input. So this would mean that we have 3 colors, so it's a color image, and we have 224 by 224 pixels. So if we do this, then we can call torch summary dot summary, we're passing in our model that we just loaded, AlexNet, and the dimension of our input is 3 by 224 by 224. And I don't remember what the one is. Does this work without the one? Okay. Was that the same output? Okay. I guess this is default by one. I don't know what the parameter is. But this is telling us that if this is our input, then the output we get at this point, oh, that's probably the batch size. So if we passed in 64 of these images, then all these things should be 64. Yeah, okay. But in our case, we're just passing in a single image. So if we pass in initial image of 3 by 224 by 224, the thing we get is 64 channels, and each dimension, or each one of these channels, is a matrix of size 500 by 55 by 55. And this tells us that the number of parameters we used here was 23,296. Any questions about this? So this is, again, this is just telling us because the kernel size is independent of the input size of each one of these images, that like if we were to put in an image or an input of a certain size, we'd get, this is telling us what the corresponding output would be after each one of the layers. So in particular, it's telling us that we go from 3 different input channels, that's the 3 here, one for each color, to 64 channels after the first layer. And that means just that the number of kernels we have, or the number of sets of kernels that we have has to be 64. And that's from what we talked about back here when we have multiple channels as input and as output. Okay, sorry for all the scrolling. This is what our model is doing. What we'll do is we'll just visualize the weights from the first dimension. So visualize the weights from the first layer. To do this, we will take a look at them, and we can access them by looking at alex pretrained.features. This is a bunch of different, this is telling us the things that we pass through in this model. We'll look at the first layer, so we'll look at index 0. And this we'll call the train convolutional layer. So it's a conv2D object. And we'll pass it into our plot first layer filters function, which we defined before. And we'll see what happens. So we know that each one of these kernels has, so there are 64 different sets of these kernels, because there are 64 output channels after we apply this layer. So we can visualize it in a grid of 8 by 8, right? I can't yet, okay. Yeah, so I'll zoom back in when we're running more code. So this is 8 by 8, and this is each one of the kernels that we're looking at. Because there's color, each kernel is a 3 by whatever dimensional object this is. And by looking at this, we can tell that something is going on here. We maybe don't know what it is so far, but there are some things that have these diagonal lines like this. We have diagonal lines in the other direction. We have vertical lines. We have circles. We have 2 circles. And each of them is a different color corresponding to this. Some of these are happening in just one dimension, and some are happening in multiple dimensions. And this is at the very least quite interesting. Now, you might wonder, maybe this isn't an artifact of the training. Maybe this has already happened just by the way we randomly initialized. So let's plot the same thing. So plot for a randomly initialized AlexNet model. So this, because we defined AlexNet as this before, that's the randomly initialized one, we can just run this code, and we'll see what the kernel weights are initially like when we randomly initialize them without any training. And it just looks completely black. This is because we randomly initialize them with small values. Maybe if you zoom in, you can like see like little squares going on here, but it's definitely not the patterns that we have up here. So whatever patterns appear here happen because of the training process. To get a sense for what these patterns are doing, let's maybe take a look at what happens when we pass an image through this first layer, and we'll see what this first layer of convolutions do to that image. So let's apply our learned convolutional kernels to an actual image. And maybe I'll zoom in again. Okay. So first we'll need to load an image. We can do this on the fly. Maybe let's like, does anyone have something that like a cat or a dog or a favorite animal or something else that you like? Is there an image that you want to see this applied to? A cat. Nice. But that's not what I wanted to do. Okay. Cool. So we can look for cat images online. Oh, the loft cat from Star Wars. That's very cute. Okay. It'll be hard to ask you for one of these, so I'll just choose one that I like. This is a very funny looking cat. So the image address is copied and it's this link. Okay, so let's go back. And if you're running this code on your own, you can choose whatever image you want. Doesn't really matter. I'm going to copy some code for loading this URL. This is stuff like whenever you want to load an image from the internet into PyTorch, you can just like get this code from online. What we're doing here is we're converting this image to a tensor, and then we're resizing it so the number of pixels is 224 by 224, which is the input size we were talking about earlier. And then we transform our image using this, and we'll look at the size of this image. So it's 3 by 224 by 224. The 3 is because this is a color image, and then we resize the number of pixels to be 224 by 224. Okay, we can also take a look at what this image is. If I just look at image, this is a large tensor because we converted it to a tensor, but we can use the function imshow to plot it. In particular, we can plot this image like so. We'll get an error because the like dimension that we naturally stored in tensor, so it's the number of channels, the like height and the width, is not the channel that this function takes. So we can just permute, or it is not the dimension that this like function takes. So we can permute it. This just means that the number of channels is the last thing, and then we have height and width here. And I'll just turn the axis off so it's more pretty, and then we can plot this. When we plot it, oh, that's terrible. I think because the initial image that we started with was like slightly wider, when we compressed it like this, it got scrunched a little bit, but nonetheless, we can apply our like process to it. So the way we can do this is by taking our train convolutional layer. This is the thing that we defined up here. I think I need to rerun it because it was actually the untrained thing that I ran last. Yeah, maybe I should just call this untrained convolutional layer. And this is the trained convolutional layer. So I'm just taking out the first layer from our AlexNet. I'll apply that to this input. So I get this applied to the image, and I'll get this as our output. If I look at what our output is, it's a tensor, and it has a gradient to it. So I'll just detach it from its gradient so that we can plot it up here. So if I run this again, and I look at the bottom of this, it doesn't have its gradient attached to it anymore, which will enable us to plot it. If I look at its shape, we actually know what its shape should be. because of the torch summary that we did up here. So we know when we pass in a 3 by 224 by 224 image, we should get 64 channels. Each channel is dimension 55 by 55. So we can check that's what we get out here. So if we print the shape, that is exactly what we get out, which is very good. So we like predicted this using the torch summary, and now you have confirmation this is exactly what happens. We can now apply our function that we wrote before just to plot each one of these. So first layer activations apply to our output. And when we do this, takes a little bit, we get something somewhat resembling a cat. And we have lots and lots of these. So, okay, this one I think is particularly crazy and demonic looking, and so is that one. That's pretty funny. Okay, so let's try to, so each one of these is doing something different. I'm sorry, what was that? Okay, maybe you didn't realize the mic was unmuted. Okay, so yes, so like this one in particular looks absolutely crazy. This one, it looks like is like highlighting places of dark color. So it's like dark on the ears and the mouth and right above the eyes. And that's kind of what's happening right here. This will be a lot of scrolling. I apologize. It might be easier if you like have your own copy of this as you do it. But you compare it like, okay, let's look at the top left output channel here. That came from the top left. I'm going to uncomment this so it's not so much scrolling. From the top left value or the kernel that we applied right there. So let's see if that we can make that make a little bit of sense to us. So it seems like when we apply this kernel, it seems probably that it's like 0 everywhere else, but we're selecting values in kind of a circle in the bottom right. Now, if we look at this image and we imagine this is the output value that we get there. So it's like taking things from the bottom left. So like this should be shifted a little bit downward when we look at this image. Or sorry, I said left. Should be shifted a little bit to the bottom right, which maybe you could squint at and imagine is there. And this seems to be taking edges, and in particular, edges that are occurring in like this wordly direction, kind of. So if I like, for example, the values here, right there, are like larger than the values over on this side. So it's like somehow detecting edges in a like down rightward direction. If you remember, the kernel for this one was completely black when we plotted it. So that means it's probably like similar values. So it's just taking an average of everything around it. And we get an image that looks like this. Maybe let's find a striped kernel or a kernel that looks like it takes out stripes from the image. So maybe this one, for example. So we'll look for things that are in the image that's in the first column and the third row down. So it's in the first column and the third row down. It looks like the thing that we're getting out of here is somewhat nonsensical, which makes sense because there aren't really any stripes going on in this direction. So we like when we apply the kernel, you imagine that we like take a diagonal here and we compare it to a diagonal right here and we compare it to a diagonal right there. And like nothing is getting selected out from it. The only like stripe patterns that we see in this input are like maybe the stripes coming out from the top of this cat's head. So we can maybe look for like stripes that look like that. So we have vertical stripes right here. This is in the fourth column and the fourth row. So if we go to the corresponding image, fourth column and fourth row, we also get something that's kind of crazy looking. So maybe that's not a good example of the like type of things that we're looking at. We could also do this the other way. So we're like, okay, this looks like a very interesting output that we get. It's very dark. In particular, the eyes look very, very dark, and the mouth looks like very bright. Let's see which kernel created this. So this is in the third column from the right and the third row down. So this is the third column from the right and the third row down. This is like taking an average of the area directly around it, which maybe makes sense about why we're able to preserve a lot of the structure in the image, but also why this value is so dark. Because if I take like an average from the surrounding area of its like eyes, we get like a dark average value there. And this, if I take an average around this area, this is quite bright because the like tongue is quite bright, which is maybe why we expect this to be as bright as we see it right there. Okay. This is, of course, like a little bit science, a little bit art. If you're designing these by hand, as I think you will do on the next homework, you'll see like how we can actually, by changing the values of the kernel, you can select out different things from it, like vertical edges or horizontal edges, or like other things like this. And I think this is very interesting because we're not doing it by hand. This was done by an actual deep learning model. And these are the type of kernels that it learned from this process. I think it's a good exercise. Clearly, I don't think I was very good at it with this particular image that we chose. But you can try playing around with different images. If you do that, you just specify a different URL here. When you specify a different URL, you can run the rest of this code and you get like different values for the different like cat images here. And maybe you can see that like different kernels are doing different things, and you can kind of compare them directly to each other by like scrolling up and down yourself without having or without watching me do it. Okay, that's all I had for today. I'm going to end